The morning of March 20th, 1942, found Major General Jacob Devers wrestling with a crisis that had already claimed countless American lives. The problem was deceptively simple to state, brutally complex to solve. How do you move 5,000 pounds of ammunition from a ship to dry land when there's nowhere to land? German forces had locked down every single port, from the frozen harbours of Norway all the way down to Spain. Desperate for answers, Devers fired off an urgent letter to MIT's Vannevar Bush. The message was raw, unfiltered. We need floating tanks, ships that can go shore to shore without ports. Can your scientists make this happen? The military brass had a standard response to such requests. Impossible. Everyone knew the rules. Trucks stayed on roads, boats stayed in water. Physics didn't work any other way. But 35-year-old yacht designer Rod Stevens saw the world through different eyes than most generals. He understood how water moved around obstacles, how a hull could slice through 15-foot swells and keep going. Frank Spear, an MIT engineer with a reputation for solving the unsolvable, had been wrestling with a problem most people dismissed as trivial. What if you could change tire pressure while a vehicle was moving? Nobody had ever done it. Nobody had even tried. And then there was Dennis Pulliston, a deep-water sailor who'd spent his life figuring out what kept things afloat when everything about the situation screamed they should sink. These three men had 38 days to turn an impossible dream into reality. The stakes couldn't have been higher. Success meant American trucks could cross the channel fully loaded. Failure meant the entire invasion strategy would collapse. At MIT's Office of Scientific Research and Development, the heavy wooden conference table bore the weight of America's most urgent problems. Vannevar Bush spread General Devers' letter across the polished surface, his fingers tracing the urgent handwriting that had arrived that morning. We need floating tanks, ships that can go shore to shore without ports. Can your scientists make this happen? The question seemed to echo through the Cambridge air like smoke from Bush's ever-present pipe. Behind those words lay thousands of Allied soldiers who had drowned, weighed down by equipment they couldn't abandon, trapped on beaches they couldn't cross. Bush understood the mathematics of amphibious warfare better than most military commanders. Every single landing craft cost $10,750. That was enough money to buy 3 Sherman tanks or equip an entire company of infantry. Yet these expensive vessels could only dump their cargo at the water's edge, leaving soldiers to carry ammunition and medical supplies across hundreds of yards of open beach, while German machine gunners cut them down from concrete bunkers. The ancient problem of amphibious logistics had killed more Allied troops than bullets. How do you get supplies from ship to inland depot when the enemy controls every port from the Channel coast all the way to Marseille? The solution demanded a type of thinking that military minds trained in rigid categories simply couldn't produce. You needed civilians, people who'd never been taught that trucks belonged on roads and boats belonged in water. People crazy enough to see possibilities where doctrine saw only impossibility. Rod Stevens Jr. walked into Bush's Cambridge office on a Tuesday morning carrying the quiet confidence of a man who'd just won the 1937 America's Cup. At 35, Stevens possessed something rare, an intuitive grasp of how water behaved around physical forms, a gift that separated true champions from amateur sailors. He could visualize pressure patterns and flow dynamics with the same precision that most engineers applied to blueprints. In his mind's eye, he could already see how a properly designed hull would cut through 15-foot swells without losing cargo or crew. The mathematical principles governing yacht racing, displacement and stability, and hydrodynamic efficiency translated directly to military logistics with deadly consequences. Frank Spear arrived from MIT's Mechanical Engineering department with sketch after sketch, covering every inch of his laboratory walls. The reserve officer had spent months obsessing over something most engineers would have brushed aside as trivial. But anyone who understood what actually happened on a battlefield knew better. He wanted to control tire pressure from inside a moving vehicle. Spear's diagrams showed rotating seals, air pressure systems, and dashboard controls that had never been successfully integrated before. In 1942, every military truck ran with fixed tire pressure, 50 pounds per square inch for highway driving, which meant certain disaster on sand or mud. Spear's vision was revolutionary. Adjust the system from 50 psi for concrete roads down to 12 psi for beach operations without ever stopping the truck. A mechanical innovation that would eventually become standard on military vehicles for the next 80 years. Dennis Pulliston completed the unlikely team. This British deep-water sailor had crossed the Atlantic in vessels smaller than Coast Guard cutters, developing an instinctive feel for what kept boats floating when physics suggested they should sink. Pulliston brought life-or-death practicality to every design decision. He'd learned through hard experience that equipment working perfectly in a laboratory often failed catastrophically when hit with salt spray and engine vibration and the crushing impact of 6-foot waves. His job meant taking Stevens' yacht racing theories and Spear's mechanical innovations and fusing them into integrated systems that would work flawlessly even under enemy fire. Bush set a timeline that defied conventional military procurement. April 21st, contract signed with General Motors. April 24th, wooden mock-up construction begins with teams working through weekends. April 27th, scale model completed for testing. May 30th, first prototype ready for water trials. 38 days from initial sketches to a floating vehicle based on GMC's proven 2.5-ton chassis, the same truck trusted by every infantry division heading to Europe. Stevens designed the hull with yacht racing precision. Welded steel construction, flat bottom, ribbed sides for stability in heavy seas. 31 feet long, 8-foot beam. Maximizing cargo while maintaining seaworthiness. His calculations proved that proper weight distribution would allow the vehicle to carry 5,000 pounds of ammunition or 25 fully equipped soldiers from transport ship to inland supply depot without requiring any port facilities or artificial harbors whatsoever. Spear's tire pressure system represented the project's most revolutionary element. Dashboard-mounted controls. Pneumatic lines, rotating wheel seals that maintained air pressure while allowing wheels to turn freely. The mathematical precision required had never been achieved in automotive engineering before, yet Spear's prototype worked flawlessly. 50 psi for highway speeds, 25 psi for rough terrain, 12 psi for sand operations, all controlled by a simple lever beside the driver's seat. Pulliston's propeller and rudder design delivered 5.5 knots in calm water, while maintaining steerage in conditions that would have swamped conventional landing craft. The mechanical integration of automotive transmission and marine propulsion and steering systems required expertise that bridged civilian maritime knowledge with hard military operational reality. The initial Army demonstration met exactly the skepticism you'd expect. Career officers trained to evaluate equipment within established categories simply couldn't envision how a vehicle that violated every fundamental assumption about land and sea operations could possibly provide military advantage. Too complicated, that was the official rejection. Trucks belong on roads, boats belong in water. The DUKW designated for its production year D for 1942, U for amphibious capability, K for all-wheel drive, W for water operation, faced bureaucratic extinction before ever proving its revolutionary potential. One final chance remained. Provincetown, Cape Cod, December 1942. 90 officers invited to witness what might be this vehicle's last operational test. The weather forecast promised calm seas and light winds across Cape Cod Bay. Perfect conditions for demonstrating an untested amphibious vehicle to skeptical Army brass. Instead, meteorological chaos descended on Provincetown with the fury of a North Atlantic hurricane. 60-mile-per-hour winds drove 15-foot swells against the Massachusetts coastline, transforming the scheduled DUKW demonstration into a life-or-death test of revolutionary engineering. The Coast Guard cutter Rose, 75 feet of welded steel, commanded by experienced mariners who'd weathered dozens of nor'easters, fought desperately against waves determined to destroy her. The veteran crew had navigated these waters for years, understanding every sandbar and current threatening small vessels in heavy weather. Yet the storm's violence exceeded their experience and their equipment's limits. Mountainous seas drove the Rose onto a sandbar 200 yards offshore, her steel hull grinding against sand with each wave that lifted and dropped her 6.5-ton weight. Radio transmissions grew increasingly desperate as the cutter began breaking apart under forces no vessel her size could withstand indefinitely. Conventional rescue operations failed with mechanical precision. Coast Guard motor lifeboats, designed specifically for rough water rescues, turned back after crews determined that approaching the Rose would result in additional casualties rather than successful evacuation. These 36-foot vessels, powered by reliable diesel engines, crewed by men who'd saved hundreds of lives in similar conditions, couldn't penetrate waves towering above their pilot houses. Navy crash boats attempted the rescue with equipment designed for recovering downed aviators in combat conditions. The shallow draft hulls and powerful engines normally provided advantages in surf operations, but the storm's intensity overwhelmed their capabilities. Each attempt to approach the Rose resulted in dangerous broaching as crosswaves caught the boat's broadside, forcing crews to retreat before their own vessels joined the cutter on the sandbar. Local fishing boats, normally capable of handling rough seas, swamped within minutes of entering the surf. Their experienced crews, men who'd fished these waters through countless storms, recognized conditions that had exceeded safe operational limits. The mathematical relationship between wave height and small boat survival had reached the point where physics, not seamanship, determined outcomes. 7 Coast Guard sailors clung to their dying vessel as it tore itself apart beneath them. Their desperate radio transmissions crackled through the static, each message more urgent than the last, describing a ship coming to pieces with terrifying speed. Every call painted the same grim picture, structural failure advancing faster than rescue operations could respond. 90 Army officers stood watching from a demonstration site on shore, growing increasingly helpless as they witnessed conventional rescue methods collapse one after another against the raw power of the sea. These were professional mariners, men trained and equipped with everything military doctrine said they needed to survive. Yet training and equipment meant nothing as their vessels split open beneath them. All they could do was wait. Guard Stevens stood among the officers, watching the tragedy unfold with the sharp, analytical mind that had won him yacht races by reading extreme weather conditions like few men could. He understood deep water sailing, understood how to find victory in the kind of brutal conditions that destroyed ordinary boats. The nightmare scenario playing out before him was exactly the kind of environment he'd designed the Duke AW to conquer. 15-foot seas, 60-mile-per-hour winds howling across the water, surf conditions that made every conventional rescue attempt look pathetically inadequate. These were the precise circumstances that would prove whether his revolutionary amphibious truck actually worked or was just an expensive dream. Stevens made his decision instantly. "He'll take the Duke AW," he announced to the assembled officers. In that moment, the entire nature of the demonstration transformed. This wasn't theoretical evaluation anymore. This was life or death. His crew moved with purpose, loading equipment with practiced efficiency. Stanley Rosenfeld, a marine photographer, joined them without hesitation. He understood exactly what hung in the balance. These photographs would either validate the Duke AW program or destroy it forever. Either way, the world needed to see what happened next. The engineers whose calculations had shaped every aspect of the vehicle's design now faced the ultimate test, one that would expose every weakness, every miscalculation, with lethal finality. The cargo space filled quickly. Emergency rescue gear, medical supplies, communications equipment, everything they might need crammed into the amphibious truck's limited hold. The Duke AW roared down the beach at 50 miles per hour, sand spraying behind its wheels as the vehicle gripped surfaces where conventional trucks would have bogged down helplessly. Stevens pushed the accelerator until the last possible second, then pointed the vehicle straight into the mountainous surf that had broken every other rescue attempt. The transition happened in heartbeats. The automotive transmission disengaged with mechanical precision. The marine propeller drive engaged. The truck became something else entirely. A hybrid machine caught between land and sea, operating in both worlds simultaneously. 5.5 knots through conditions that would have swamped vessels 3 times its size. The flat-bottomed hull rode over the waves rather than plunging through them, each surge lifting the vehicle instead of crushing it. The ribbed sides held firm, preventing the dangerous rolling that would have capsized smaller boats. The propeller and rudder systems maintained control despite the chaos, keeping the truck pointed toward the dying ship, while seas continued their assault. It was engineering married to seamanship, decades of Stevens's racing experience combined with pure mechanical innovation. The rescue demanded absolute precision. Stevens had to maneuver alongside the foundering vessel while both craft rose and fell through the wave cycles that threatened to smash them together. Waves crashed across both hulls simultaneously. Water flooded into the cargo compartment as the DuKW's watertight integrity was tested against the ocean's relentless pressure. One sailor at a time, Stevens's crew pulled the Coast Guardsmen aboard. 7 men, each one pulled from certain death, into the precarious safety of the amphibious truck. The last man had barely made it aboard when the Coast Guard cutter's hull finally gave way. Hours of structural failure ended in violent collapse. The return journey proved the DuKW's complete transformation. Loaded beyond normal capacity with rescued personnel and emergency equipment, the vehicle maintained its speed and stability through seas that continued threatening every conventional rescue craft on the water. The transition back to land operation happened seamlessly. The propeller drive disengaged. The 6-wheel automotive drive resumed. The DuKW climbed the beach and deposited everyone safely onto dry sand, where medical personnel and astonished Army officers waited. Rosenfeld captured every frame: the initial entry into the surf, the maneuver alongside the sinking ship, each Coast Guardsman being pulled to safety, the final triumphant return to shore. Within hours, he boarded an express train carrying those photographs to Washington, racing through a winter landscape toward the Pentagon. The visual proof traveled faster than bureaucratic skepticism could travel. Within 24 hours, military officials were looking at images that made all the theoretical arguments irrelevant. 7 Coast Guardsmen alive because an impossible vehicle accomplished what nothing else could. Major General Jacob Divers held those photographs in his hands, and his faith in civilian innovation, a faith that had isolated him from conventional military thinking, suddenly looked like visionary leadership. He was the only high-ranking officer who had supported this project from the beginning. Now he possessed irrefutable evidence that his judgment had been sound. The images circulated through military headquarters with unprecedented speed, reaching decision-makers who had previously dismissed the amphibious truck as an expensive experiment. Each photograph documented specific moments of salvation: the DuKW driving into mountainous surf, maneuvering alongside the dying vessel, evacuating 7 men who would have perished without intervention. Abstract engineering discussions became irrelevant. These images told a story that no technical specification could match. Visual proof of life-saving performance under extreme conditions replaced every bureaucratic argument. October 1942 brought the decision: official adoption of the DuKW into Army procurement, mass production contracts awarded to General Motors facility in St. Louis, Missouri. Military thinking reversed course completely. The vehicle previously rejected as unnecessarily complex suddenly became essential. Divers's endorsement, backed by photographic documentation, carried weight that no staff officer could dismiss. By the end of 1942, production units began rolling off assembly lines that had been converted from civilian automobile manufacturing. The St. Louis facility that once produced Chevrolet sedans and Buick coupes now focused entirely on welding steel hulls and installing marine propulsion systems. 3 civilians had revolutionized amphibious warfare in 38 days. Now American industry was tasked with mass-producing that revolution. Throughout 1943, manufacturing accelerated with unprecedented intensity. Military planners recognized the DuKW's strategic importance. 5,000 units emerged from General Motors facilities that year alone. Each vehicle represented 10,750 of precision engineering, combining automotive reliability with marine capability in ways that seemed to violate the basic rules of vehicle design. Many of the production line workers were women who had replaced male employees serving in combat units. They mastered complex assembly procedures, integrating Stevens's hull design, Spear's tire pressure system, and specialized marine propulsion components into unified amphibious vehicles. The St. Louis plant reached peak production during 1944, delivering 10,000 UKWs as Allied forces prepared for the largest amphibious operation in military history. The manufacturing process required coordinating dozens of subcontractors producing specialized components: marine propellers from Michigan, steel hulls from Pennsylvania, tire pressure control systems from Massachusetts. Each vehicle demanded quality control standards exceeding civilian automotive requirements. In combat conditions, failure meant death, not inconvenience. The final production total reached 21,137 vehicles, the largest procurement of specialized amphibious equipment in military history. Each UKW cost approximately $10,750 to manufacture, but in contemporary purchasing power, that represented nearly $170,000 per vehicle. The total program investment exceeded $3.6 billion. The expenditure reflected military recognition that revolutionary innovations required substantial financial commitment to achieve strategic advantage. Sicily provided the UKW's first combat test during Operation Husky in July 1943. Allied forces faced the eternal amphibious warfare problem: how to maintain supply lines from offshore transport ships to inland ammunition dumps when German forces controlled every port facility. Traditional landing craft could deliver cargo to beaches, but then required separate vehicles to transport supplies 20 miles inland to forward operating bases. Infantry and artillery units desperately needed ammunition, medical supplies, replacement equipment. The vulnerable chain of transfers exposed everything to German artillery fire. The UKW eliminated this critical weakness entirely. Each vehicle drove directly from ship to supply depot without stopping at the waterline. Each carried 5,000 pounds of essential cargo across beaches still under intermittent German fire, then continued inland through terrain that stopped conventional trucks cold. Supply lines that previously required multiple transfers and exposed beach operations now functioned as seamless operations. Fewer casualties, increased delivery efficiency. Combat performance exceeded every theoretical projection. The UKWs operated successfully in surf conditions that prevented normal landing craft operations, maintaining supply flow during rough weather that traditionally suspended all amphibious work. Their six-wheel drive capability handled soft sand and muddy terrain that immobilized standard military trucks. The tire pressure control system allowed instant adaptation to changing ground conditions without stopping to manually adjust individual wheels. The vehicles proved equally valuable for casualty evacuation. Rather than carrying supplies forward, they transported wounded soldiers from forward positions to hospital ships anchored offshore. This dual-purpose capability eliminated the need for separate medical evacuation systems, simplifying logistics while providing critically wounded personnel with faster access to surgical facilities that could save their lives. German forces initially couldn't comprehend how Allied supply operations continued functioning. Intelligence reports from captured documents revealed confusion about American logistics capabilities. The UKW operated so differently from conventional landing craft that German tactical doctrine provided no effective countermeasures for vehicles transitioning seamlessly between land and sea operations. By the end of 1943, UKW production had reached full capacity. Military planners began preparing for Operation Overlord, the cross-channel invasion that would determine whether Allied forces could establish permanent footholds in Nazi-occupied Europe. Sicily had demonstrated tactical capabilities. Normandy would test whether Stevens, Spear, and Polston's revolutionary design could handle strategic-scale operations involving hundreds of thousands of troops and millions of tons of supplies. The stage was set for ultimate validation. The men who had ignored conventional wisdom about trucks and boats would soon discover whether their 38-day miracle could help win the largest battle in human history. Operation Overlord demanded logistical precision exceeding any previous military undertaking. 2,000 UKWs received assignment to the cross-channel invasion. Their strategic deployment was calculated with mathematical accuracy, reflecting the operation's total dependence on sustained supply flow. 12 companies would support Omaha Beach operations, where German defensive positions threatened to annihilate Allied forces before they could establish permanent footholds. 7 companies would reinforce Utah Beach, where paratroop units required immediate resupply to maintain their precarious inland positions. Each UKW carried 5,000 pounds of ammunition, medical supplies, and artillery shells that would determine whether 150,000 Allied soldiers survived their first day on Nazi-occupied soil. These vehicles represented American industrial mobilization concentrated into amphibious form. The manufacturing facilities at St. Louis had built these particular vehicles during spring of 1944, with each amphibious truck reflecting hard-won knowledge extracted from the grueling Sicily campaigns. Stevens's original hull design underwent significant refinement based on combat reports documenting stability challenges and deterioration problems, while the tire pressure management system now incorporated redundant safety features that kept the vehicles operational even when primary systems sustained battle damage. The propulsion package benefited from strengthened corrosion protection after Mediterranean operations exposed serious weaknesses in saltwater resistance. When June 6, 1944 arrived, the meteorological forecast presented a dire picture. Military planners faced an agonizing decision as storm systems threatened to derail the largest amphibious assault ever attempted in military history. Towering waves churned across the English Channel with enough force to sink conventional landing craft. Wind gusts threatened to scatter paratroopers across the French countryside. Every standard safety guideline for amphibious operations stood violated by the actual conditions. Yet postponement carried its own catastrophic risk. The narrow window of favorable tides would not return for weeks, giving German defenders precious time to fortify the Atlantic Wall beyond any hope of Allied penetration. The first assault troops hit Normandy's beaches at 6:30 a.m., plunging into water that bucked and thrashed against assumptions about what amphibious warfare could actually accomplish. German gun positions in concrete emplacements controlled every yard of sand from waterline to clifftop. Artillery and machine gun fire created zones of pure devastation that turned the open beach into a hellscape for anyone attempting to advance. Behind the initial waves came the amphibious trucks. 30 minutes after the first soldiers touched shore, the UKWs roared across the Channel's violent waters, their engines straining against seas that would have swallowed any ordinary vessel. These rough terrain vehicles carried ammunition and medical supplies, the lifeblood that would determine whether the beachhead could survive its first critical hours. Each DUKW represented a lifeline connecting supply ships anchored offshore to infantry units fighting inland with ammunition supplies that dwindled by the minute. The transition from ocean to sand happened under direct fire. German artillery had already registered these very waters for maximum destruction. Machine gun rounds sparkled off steel as explosions erupted nearby, sending columns of sand and seawater skyward, obscuring everything and forcing drivers to navigate by instinct alone. The vehicles shifted into six-wheel drive as they climbed the beach, their specially designed low-pressure tires gripping sand that would have stopped conventional trucks dead. They pushed forward, carrying essential material toward ammunition dumps positioned beyond German observation posts. During that opening 24 hours, these vehicles performed logistics feats that nobody had truly believed possible. 3,000 tons of critical supplies reached forward positions, while German forces concentrated their heaviest firepower against vulnerable beachheads. Constructing artificial harbors would have consumed 6 months before providing equivalent supply capacity. Months the invasion forces did not possess. The UKWs solved the problem through revolutionary design that eliminated the need for elaborate port infrastructure. Supply operations accelerated dramatically as the week progressed. 150,000 Allied troops now pressed inland from their foothold, and the vehicles ferried loads constantly between offshore transports and forward depots. Ammunition, fuel, rations, replacement equipment, everything flowed through this amphibious supply network while German forces desperately attempted to choke it off. The vehicles made trip after trip, maintaining the delivery schedules that kept combat units fighting effectively. 90 days of Normandy fighting produced unprecedented logistics achievements. 3 million tons of material moved through the UKW system, everything from individual cartridges to complete artillery pieces. These numbers represented far more than mere tonnage statistics. They embodied the strategic advantage that allowed a relatively modest invasion force to overwhelm larger German defensive armies through supply superiority that ground German defenses into collapse. Then catastrophe struck. During the June 19th through the 22 period, a massive storm system arrived with unprecedented fury. Winds reached hurricane velocity while waves demolished Mulberry A, the artificial harbor considered absolutely essential for continued operations. Conventional landing craft became completely unusable as the tempest created conditions that violated every established safety protocol. The DUKWs continued working throughout those 4 devastating days. Stevens's stable hull configuration handled the punishment. Spear's tire pressure system adapted perfectly to the soft sand. Polysteen's propulsion components kept functioning when everything else failed. 6-wheel drive tackled the sand liquefied by relentless rain. The amphibious capability maintained contact with offshore supply ships when normal landing craft operations became impossible. This hidden crisis illuminated the DUKW's true strategic significance. Here was operational flexibility that transcended weather conditions that normally shut down military activities completely. German defensive planning had relied on periodic isolation of beachheads from supply sources whenever storms disrupted operations. Yet the DUKW system continued uninterrupted while conventional logistics collapsed. The breakout from Normandy succeeded because ammunition never ran short. Medical supplies kept flowing. Equipment stayed functional. German forces could not interdict supply lines that operated regardless of weather. Logistics determined victory as surely as firepower or tactical brilliance. Superior engineering had delivered superior strategic advantage. Victory arrived on May 8, 1945, when German surrender documents were signed in a French schoolhouse, concluding 6 years of warfare that had consumed 60 million lives. The final accounting revealed staggering numbers that military historians would analyze for generations. DUKWs had delivered approximately 5 billion tons of the 15,750,000 tons of supplies that reached European battlefields. 1/3 of everything that enabled Allied victory traveled through amphibious supply networks created by 3 civilians working frantically during spring of 1942. This represented far more than moving cargo from point A to point B. Every pound delivered by DUKW eliminated the need for conventional logistics requiring artificial harbors, multiple transfer points, extended vulnerable supply lines. Traditional amphibious operations would have demanded 6-month harbor construction before matching these supply flow rates, delays that would have permitted German forces to strengthen Atlantic Wall defenses beyond Allied assault capability. Stevens's hull design proved seaworthy enough to cross the English Channel fully loaded during combat operations, validating yacht racing principles applied to military logistics with precise mathematical accuracy. The flat bottom with ribbed sides managed 15-foot seas while carrying maximum cargo weight, demonstrating hydrodynamic efficiency that conventional landing craft could never achieve. Weight distribution calculations maintained stability and controllability in surf conditions that would have capsized traditional amphibious equipment. Spear's tire pressure innovation truly changed everything about military vehicle design. The dashboard-controlled system adjusted pneumatic pressure from 50 pounds per square inch for highway speeds down to 12 psi for beach operations, eliminating mobility restrictions that previously chained military trucks to prepared roads. Every vehicle manufactured after 1945 incorporated variations of Spear's rotating seals and pneumatic controls, making his wartime innovation a permanent feature of automotive engineering, extending far beyond military purposes. Polystein's propeller and rudder integration created marine propulsion that functioned reliably under actual combat conditions rather than theoretical laboratory settings. His deep-water sailing background had translated into mechanical systems that survived salt spray, engine vibration, and the crushing impact of heavy seas while maintaining the 5.5 knot speeds essential for tactical mobility. These propulsion systems operated flawlessly through Mediterranean campaigns, Atlantic crossings, and Pacific operations, testing every design assumption about amphibious reliability. The 3 innovations perfected during that frantic spring created synergistic capabilities exceeding any individual component's contribution. Stevens's hull provided the platform. Spear's adaptive mobility system functioned on that platform. Polystein's propulsion enabled both concepts to work in the maritime environment. Successful integration demanded civilian thinking, unbound by military doctrine, separating land and sea vehicles into different categories. 21,137 DUKWs rolled off St. Louis assembly lines during peak production years, each representing industrial mobilization, prioritizing revolutionary innovation over conventional military equipment. The total program cost of $3.6 billion purchased strategic capability that traditional procurement processes could never have delivered regardless of funding. Conventional landing craft production could not provide the operational flexibility enabling sustained supply during the June storm when alternative logistics methods disappeared completely. After Germany's surrender, most vehicles faced immediate scrapping as military budgets contracted and demobilization took priority over equipment preservation. The amphibious trucks that had enabled victory became surplus inventory sold to civilian operators, recognizing construction and emergency services applications. Thousands disappeared into scrap metal dealers who valued steel content more than revolutionary engineering, erasing physical evidence of innovation, transforming warfare's fundamental nature. The three designers resumed civilian careers, receiving minimal public recognition for achievements significantly influencing military history's course. Stevens returned to competitive yacht racing, applying hull design principles developed during military work to racing sailboats that continued capturing championships. His America's Cup background had prepared him for the DUKW project, but wartime innovation had sharpened his understanding of hydrodynamic principles separating winning designs from mediocre ones. Polystein authored sailing manuals, sharing deep-water navigation techniques with recreational mariners, translating combat-tested seamanship expertise into civilian applications, improving small boat safety standards. Wartime integration work had required mastering mechanical systems beyond traditional sailing knowledge, creating expertise, benefiting military and civilian maritime communities through publications becoming standard references for decades. Spear pursued subsequent military innovations, solving operational problems through mechanical engineering excellence, though none achieved the strategic impact of his tire pressure control system. His later patents covered vehicle suspension, communications equipment, and specialized tools improving military effectiveness through attention to details others overlooked or dismissed. When Korean war fighting erupted in 1950, DUKWs returned to combat for amphibious landings, where their amphibious capability proved essential for establishing beachheads without port facilities. These same vehicles that had enabled D-Day victory demonstrated continued relevance against different enemies in different theaters, validating design decisions made 8 years earlier by three men rejecting conventional wisdom about military vehicle limitations. Their legacy appeared throughout American cities in unexpected forms, with duck tours carrying tourists through downtown streets and harbor waters using essentially identical designs that had won World War II. Civilian applications demonstrated public recognition of engineering excellence, transcending military origins, proving revolutionary innovations often found new purposes beyond original requirements. Spear's tire pressure system became standard on every military vehicle produced after 1945. From jeeps to main battle tanks, ensuring his wartime innovation influenced military mobility for subsequent generations. Mechanical principles pioneered under wartime pressure became foundational technology, improving vehicle performance across conditions ranging from desert sand to Arctic tundra. Their achievement embedded lessons extending far beyond military applications to fundamental questions about innovation and institutional thinking. Three men rejected expert opinion, challenged conventional wisdom, and created what seemed impossible through civilian approaches to military problems. Their success demonstrated that revolutionary thinking often originated with outsiders lacking professional training, teaching why new ideas couldn't work. Enabling breakthrough innovations experts had deemed theoretically impossible, yet practically essential.